So originally, I was the first half of a collaboration with Miguel to cover the Bootstrap, but I'm really not going to get too far into the Bootstrap today and tomorrow. I'm really going to be going over what I guess are sort of CFT basics from a different direction than Sylvia. So you're not going to see any magnets in my talks. So let me make some disclaimers first about sort of the scope of what I'm going to discuss and the assumptions I'm going to be making more or less all the time. So first, my talks are going to be in Euclidean signature. So as Sylvia said, CFTs come to us sometimes in Euclidean signature, sometimes in Lorentzian signature. However, our focus will be theories in Euclidean signature that are related to unitary Lorentzian theories. So these are theories that you get by starting out with a unitary theory in Lorentzian signature and then Wick rotating into Euclidean signature. And we'll see the technical consequences of that eventually. I will assume a certain kind of locality in the theories that we're talking about. So this could, if you had a Lagrangian description for a theory, amount to having a local Lagrangian. But we're not going to talk much about Lagrangians. So the main avatar of locality that I'm going to use is the existence of a stress tensor as a local operator in my theory, which encodes the way that I infinitesimally change the metric at a point in space. And finally, the next two lectures today and the first lecture tomorrow that I give will be very abstract, which is either an apology or a promise. And this is the sense in which this is really the beginning of a course on the Bootstrap, is that I'm not going to write down any Lagrangians. I'm not going to write down any lattice models. I'm going to describe the features of a quantum field theory, which is conformally invariant, that arise sort of out of pure general thought. And that is going to be the starting point for a lot of the more specific numerical analysis that Miguel and other people might talk about. Okay, so with that preamble out of the way, I don't like this chalk very much. The first thing that I want to talk about is symmetries. So Sylvia defined a conformal field theory as a quantum field theory which is invariant under conformal transformations. Symmetries are some sort of foremost aspect of these theories. And conformal transformations, conformal symmetries, are examples of space-time symmetries. They're symmetries that move points around in space. And so I want to talk a little bit about space-time symmetries, and in particular the sense in which they arise from the stress tensor. And the first part of this is going to be a review from any basic QFT course, but I want to make sure that everyone is thinking about these things in sort of an appropriately abstract way. So I said I'm interested in quantum field theories that have a stress tensor which I will define in the sense that I will define how it appears in correlation functions with other local operators in terms of variations and this could be in a correlation function expectation value when there's some background metric in space-time, which is what I'm calling G. So this is the operator statement that says that a stress tensor tells me how I infinitesimally change the background metric. If I'm doing a small variation of the background metric at a point x, up to these prefactors that I've chosen presciently, that is what I mean by inserting the local operator t at that point. And famously, the stress tensor is a conserved operator. This is an operator equation. And what I mean by calling it an operator equation is that this is something which is true in correlation functions with the possible exception of contact terms, meaning that this derivative is 0 unless I'm inserting this thing that's supposed to be 0 at the same point as some other operators already located. And something that is a good exercise for everyone who hasn't done it before is to check that using this definition of the stress tensor, so minus sign, that that you get very particular contact terms on the right-hand side. So this is going to be 0 unless x coincides with one of these other xi where the operators are inserted. And this is something that you can derive if you are interested. You can derive this by demanding that your theory be diffeomorphism invariant. So this comes from considering a change of the metric, which is actually induced by a diffeomorphism. OK. And what does this have to do with symmetries? Conserved currents, you hopefully know, are ultimately related to symmetries, and in particular to conserved charges. Because the conservation condition allows us to define a charge associated to a codimension 1, so a dimension d minus 1, surface or hypersurface inside of space, which is the integral over that surface contracted of the normal of the surface contracted with the stress tensor. And then defining such a surface operator or hypersurface operator, you get something whose dependence on the hypersurface is topological, meaning that I can continuously deform this hypersurface and nothing changes if I've inserted that in correlation functions by Stokes' theorem, because changing it amounts to taking the integral of the divergence of this thing over the difference between the surfaces. OK, so these are the same conserved charges that you already know and love. In particular, this thing that I've defined here that has a free nu index is related up to conventions up to conventions about overall normalization to the charge that measures momentum. So more generally, I had this free index. So for any vector field, epsilon, which in an orthonormal basis looks like this, I can try to define a conserved charge the same way ds mu epsilon nu t mu nu. And this thing will be topological in the sense that the thing inside is conserved, and so I can change sigma and pick up 0. If the thing I get when I use Stokes' theorem is 0, but T mu nu is symmetric and conserved, so this is true if and only if. This equation holds, and this is the killing equation. So this tells me that if I choose my epsilon to be a killing vector for my background, then I get a symmetry. This is something that you know. Killing vectors generate isometries, and isometries are symmetries, and those symmetries have conserved charges. This is just the sort of abstract version of those statements. So in particular, in d-dimensional Euclidean space, the killing vectors are the ones associated with translations, which I will normalize this way, and the ones associated with rotations that I will normalize this way. And these lead to conserved charges that go by the capital letter versions of the same names as their killing vectors. And those are just the momentum and angular momentum charges that you know and love. Okay. Okay, so this was a rehash of some just completely general QFT basics that I've gone through not only to have names for these charges, but also because we can now understand, at least roughly, these statements that Sylvia was making, that if you have a theory which is a renormalization group fixed point, so in particular, if it's scale invariant, then you should sort of, there are caveats that I'm going to discuss, then you should get a bunch of extra symmetry in the form of this so-called conformal symmetry. So we want to introduce scale invariance. We want to consider theories in this abstract language of the type that Sylvia was discussing that occur at second-order phase transitions or at fixed points of the renormalization group. And if I am at such a fixed point, then I should have a relationship between some correlation function of local operators in flat space with a fixed metric that I've named eta mu nu. And an identical correlation function, nearly identical correlation function, where I have rescaled space. So I've now changed the overall scale, but Silvio told us that there's no intrinsic scale. So my theory shouldn't know that I've changed the overall scale by changing the background. But my local operators might transform under this identification. So this is this anomalous scaling that we were talking about. These operators may have some anomalous dimensions, or even just some dimensions. And that means they will be related in some fixed way between the original theory and the rescaled theory. And now you can consider the invariance. You can consider this invariance condition under an infinitesimal rescaling. So lambda, this rescaling parameter on the metric is just infinitesimally close to the unit. And then I use the fact that I know how to infinitesimally change the metric in terms of insertions of the stress tensor. And I'm inserting a variation of the metric that looks like a constant times the flat space metric. So that thing contracted with the stress tensor gives me the trace of the stress tensor. And this variation, so this with an epsilon up front is the variation. This should be 0 except for the possibility of contact terms, which is related to this fact that these O's turned into O primes. So there's some infinitesimal transformation of the individual operators. These were just on the original background. So this equality is the condition that I obey this sort of rescaling symmetry infinitesimally. And you see that this looks like an integrated version of what I had over here. Over here I had the requirement that T mu nu was conserved as an operator equation, and that meant that in a correlation function I only worried about contact terms. This looks like what I would get if I integrated this kind of an equation where instead of d mu T mu nu, I just had the trace of T over all of space-time. And the claim that we all believe is that this is how you should interpret this equation in general. So generally speaking, this integrated equation is supposed to be the integrated version of a true local equation that T mu mu is equal to 0, again, as an operator equation that can be corrected by contact terms. And the reason I'm using so many weasel words as I say this is that this doesn't actually follow immediately, because it could be that the trace of the stress tensor is a total derivative for some vector operator called V. And then by integrating by the integral of a total derivative being 0, again, not worrying about contact terms because I've already absorbed them, you could still end up with this integrated version of the equation. Okay, so this happening is known as having scale but not conformal invariance. And as is implied by that way of referring to it, we think that that's the special case. Having scale but not conformal invariance is the special case, and generally, such an operator should not appear on the right-hand side. There's an interesting timeline of this belief, and there are a number of arguments that apply in various special cases. Like Silvio, though, now that I've introduced this possibility of things going badly, I will assert that I'm not interested in the case where things go badly. So, being at one of these scale invariant fixed points, as long as I'm willing to believe that there are some plausible sounding arguments that I shouldn't generally be able to find such an operator V mu who appears on the right-hand side of the trace of the stress tensor, it gives me this new this new condition on the stress tensor, this new nice condition. And that allows me to generate more conserved charges. Did I want to say something else first? Yes. Notice, before talking about charges, notice that having this honestly be 0 means that at least infinitesimally that I can do a change of the metric, which is not just this overall scaling that I was doing here, that integrated T mu nu over all of space-time with a constant coefficient. But if T mu nu is 0, then I could have also had an epsilon of x in here. And so I could have been doing a position-dependent rescaling of the metric. So a theory that has this traceless stress tensor is actually Weil invariant, Weil rescalings being changes of the metric by an overall scalar factor that depends on position like this. And I've put a big asterisk here because famously this symmetry can be anomalous. There are so-called Weil anomalies that are interesting and useful and that I also won't talk about for the rest of my lectures because they won't play a major role quantitatively. The important thing to know is that the Weil anomaly is under control. So even though this symmetry can fail to be true for finite Weil transformations, its failure is something that you can quantify and understand. And therefore you can still do Weil transformations in a theory which has a traceless stress tensor, is infinitesimally Weil invariant, has a Weil anomaly. You can just write down the corrections from the anomaly. But we won't need to, so it'll be fine. Okay. So that was one sort of new symmetry that I get from the tracelessness of the stress tensor. I get Weil symmetry, but what I prefer, and maybe this is just me, what I prefer is symmetries that relate observables in a fixed background. So this Weil invariance, this Weil symmetry allows me to relate observables where I change the background metric. So Weil invariance relates different backgrounds but it implies symmetries of a fixed background. And that's because I can now consider diffeomorphisms whose action on the metric is an overall Weil transformation in fixed coordinates. And whereas before those wouldn't have been symmetries because they would need to change the metric, now I can undo the Weil transformation because I have Weil symmetry. So let's see, those were words. The infinitesimal version of this can again be thought of in terms of this idea of constructing charges using the stress tensor. I had this equation before, and then I said that I should have said without knowing more, I have an if and only if. I need this equation to be true. But notice that if T mu nu is traceless, then I can also solve this equation if d mu epsilon nu plus d nu epsilon mu is proportional to the flat Euclidean metric. Because then this contracts with the stress tensor and gives 0. And this is the conformal killing vector equation. And so the claim is that I would have new conserved charges and corresponding symmetries associated to conformal killing vectors. And in any dimension D, there are some standard conformal killing vectors, standard solutions to this equation. One I'll call D, and one dplet I will call K mu. And the charge I build using this D killing vector, I will call capital D. And it is known as the dilatation charge, or the generator of dilatation symmetry. And the thing that I build with these Ks, again, will be the capital version. And these are the generators of these special conformal transformations that Sylvia wrote down the equation for that looked sort of wacky. And now you can sort of see why you get a weird-looking transformation of spacetime. It's because it's generated by this weird-looking killing vector that was the other solution of the conformal killing vector equation. And as an obligatory comment, probably many people already know that in the special case when D is equal to 2, there's actually an infinitely larger set of solutions to the conformal killing equations. And this leads to the fact that CFTs in 2 dimensions are very special. But I'm not going to talk about 2 dimensions. OK. I'm sort of going back and forth.
Chris,
Yeah.
you can erase this.
Oh, I can erase this. Everyone already on Wi-Fi? Beautiful. OK, so how do we think about these transformations, either the infinitesimal versions encoded in these diffeomorphisms generated by these conformal killing vectors, or their finite versions? OK, so what are these symmetries? Well, a good indicator is to look at the Jacobian of the change of variables. Of the change of variables of this type. And this is a pretty simple exercise. That you can then massage a little bit. And even more, so remember that this quantity was this thing we called C of x. It was this Weil rescaling of the metric that we got, was induced by this diffeomorphism. So up to order epsilon squared things, the Jacobian of the transformation looks like this, where you can now see that this is an infinitesimal rescaling. It's just multiplying by this number. And this we recognize as an infinitesimal rotation. So these conformal transformations, including these weird special conformal ones, are diffeomorphisms, they're changes of coordinates that act locally as some combination of local rescaling and local rotation. And we can exponentiate and write the finite version. So this was for an infinitesimal transformation, but then we can integrate those vector fields and end up with a finite change of coordinates. And in that case, the Jacobian is again a rescaling times a rotation, where now these are finite rescalings and rotations. So omega of x is some rescaling. It's a map into the positive reals. And O of x is a position-dependent element of the rotation group. Okay, and these are, because it acts this way as some combination of rescaling and rotation at every point, this means that a conformal transformation preserves angles, because the notion of orthogonality at each point is preserved. So people sometimes describe the conformal transformations as the angle-preserving changes of coordinates of your space. Okay. So it's useful to know. So this is the way that the Jacobian behaves under finite conformal transformations. It's useful to know what the actual finite conformal transformations look like. Unfortunately, the complicated one, Sylvia ruined for me by already writing it down. But I'm still going to talk about it. So these finite conformal transformations map points according to sort of the exponentiated action of these conformal killing vectors, or even ordinary killing vectors that I wrote down before. So this is just an ordinary killing vector that generates translation. I had these mu nus that can get contracted with a matrix that sends x mu to e to the w mu nu x nu. So if I choose a matrix of anti-symmetric matrix of parameters to contract with these rotational killing vectors, then I just get the exponentiated rotation matrix. The dilatations, as implied by the name, are just these rescalings. They send points to some multiple of themselves. And then there's this weird transformation that Sylvia already wrote down, so I will write it down as well. Let me write it for an index. I actually like it with a plus sign. That's no different. And now, a question that you should ask yourself is, if there's a good way to think about this funny special conformal transformation, because if you look at that equation and you know how to think about it, then you're very impressive. Generally, it's a weird-looking equation. And I'm going to deliver to you the answer now, but proving that this is the right way to think about it is one of the exercises on the problem, so you should try to prove it. And in order to, in order to understand it, we need a quick aside on inversions. So consider the following map from RD minus the origin to RD minus the origin. You can also think of this as the map from RD plus the point at infinity to RD plus the point at infinity. This ends at point x to its reflection through the unit circle. So it sends the origin to infinity and infinity to the origin, which is why you need to either subtract or add points at 0 or points at infinity. Now you can check that the Jacobian for this change of transformation, change of variables, or this diffeomorphism looks like this, where this is a rescaling, and this is an orthogonal matrix. And in fact, this is in OD and not SOD. So this is an orientation changing element of OD. So this is a conformal transformation, but it's not connected to the identity. In particular, you can tell this not connected to the identity because you ended up with your orthogonal matrix in the Jacobian being in the disconnected component of the orthogonal group. Whereas when you exponentiated things, you had to get something that lived in the connected component of the orthogonal group. And because Leonardo demanded it, this particular orthogonal matrix will be called I mu nu, and it is named the inversion tensor. And it is very useful for doing calculations in conformal field theory. Okay, so the point of introducing this, so this is something that doesn't follow from any of these local considerations with killing vectors. So in particular, it turns out to be the case that a conformal field theory does not have to be symmetric under inversions. But for the purposes of looking at transformations just of points in space, we can use it as a tool. And you can prove, without an enormous amount of work, that this special conformal killing vector is the conjugation of the translation ordinary killing vector by inversions. And similarly, and you also need to do a calculation or at least an argument to show this, the exponentiated version of finite special conformal transformation is the conjugation by the inversions of finite translations. So this tells us, I claim, or this should make you feel like you understand how to think about these special conformal transformations, because you're flipping around 0 and infinity and then doing a translation. So the point that was infinity becomes the origin. You do a translation. That moves the origin, your new origin. It leaves fixed your new infinity, which was your old origin. And then you transform back. So this is like the opposite of a translation that moves the origin and fixes infinity. This moves infinity and fixes the origin. In particular, you can see that moves the point at infinity to the point B over the norm of B squared. Yeah. Okay. Questions at this point? So finally, we have a collection of infinitesimal and finite conformal transformations, which are the things that we have been instructed to care about if we happen to be studying a theory that has a traceless stress tensor, which we are probably doing if we're studying one of these fixed point theories. And the last sort of purely symmetry question that I think you should ask before we start asking about how this actually manifests itself in the context of a quantum field theory is what is the symmetry algebra? So we have a bunch of diffeomorphisms, or algebra or group, depending on whether we're looking at the infinitesimal or the finite versions. We have a bunch of these vector fields. Correspondingly, we have a bunch of charges. We can ask what the algebra of these things is. So I'm going to phrase this in terms of conserved charges. If I take one of my charges associated to one conformal killing vector and commute it with a charge associated to another killing vector, then, well, the way it works out in this case is that the algebra of the charges is determined by the Lie algebra of the vector fields. And here there's another disclaimer that this is not absolutely guaranteed for you. And it turns out that in 2 dimensions, where you have an infinite dimensional algebra, because I told you there are many more conformal killing vectors, the algebra of the charges turns out to be a central extension of the algebra of vector fields. But in this case we're working in more than 2 dimensions, or in 2 dimensions where we only work with sort of the set of killing vectors that I've claimed to care about, you don't run into any of those subtleties. And I should comment at this point, in case it's not familiar to everyone, on exactly what I mean by the commutators of these charges, because when I introduced them, perhaps in a way that you've all seen before, or perhaps in an unfamiliar way, I claimed that I want to think about these charges as sort of things that live on codimension 1 surfaces in spacetime, and that only depend topologically on how they're inserted in spacetime. So this is related to, but not exactly the same thing as what you would do in sort of canonical quantization, which might have been where you've seen these charges more frequently. So I can explain in pictures what I mean by this commutator of charges. So suppose I have some surface, and I'm inserting the charge associated with killing vector epsilon 1 on it, or I'm inserting q epsilon 1 on it. And then I try to insert q epsilon 2 sort of right on top of it, just right next to it. There's an ordering here, and I can compare it with a minus sign to the case where q epsilon 2 is on the inside and q epsilon 1 is on the outside. And this is a commutator. This is what this means. In correlation functions, if I've inserted these things on sort of adjacent slices, then the result will be related in this way. So this, in the case where my hypersurface is just a flat slice, and I think of it as sort of the flat slice where the Hilbert space of a unitary quantum field theory would live, this just corresponds to the usual notion of time ordering of the insertion of charges. So what that leaves for me to do is to write down what the actual algebra is, because I have the explicit killing vectors. So it's just algebra to write down the commutation relations for the charges. And I guess I'll do it. the most annoying one to write. Well, maybe I won't write this one. So the mu nus are the ones that just generated ordinary rotations. So this equals the right SOD commutator, because it's 4 terms long, and I don't want to write all 4. Mu nu acts as a rotation on momentum. Del mu minus del mu rho p nu. It also acts as a rotation on the vector of special conformal charges. It's the same with p's changed with k's. The more important things, in the sense that these are not things that you would immediately know, at least you wouldn't know the right signs, and they end up being relevant down the line, is that the dilatation operator sort of diagonalizes the momentum generator with a factor of plus I, and the special conformal generator with a factor of minus I. And finally, commutator of special conformal and momentum is a combination of rotation and dilatation. And now, this isn't something that will immediately jump out to you unless you are amazing at seeing commutators. But it turns out that if you define some renamed charges, I want this to be mu. And L minus 1, 0 is equal to D. And you define these things to be antisymmetric. So you've defined all of them. Then these things generate the conformal algebra, which can now be identified as SO D plus 1, comma 1. So I had SOD, and I get 2 extras from the 0 index and the minus 1 index that I've defined in this way. So the conformal algebra is a totally reasonable, simple algebra. It just acts on space-time coordinates in a complicated nonlinear fashion. OK. When did I start? At 11. OK, good. So this was symmetries. This was part 1, symmetries. Now I'm going to start part 2, operators. I finished part 1 faster than I thought, which means it would be too early to take an impromptu break. But I am going to take a break at some point in the middle of part 2, because
maybe now it's a good time for questions.
Questions are, all times are good times for questions. But yes, now, if anyone has questions. Nice try. OK. So the claim, we started out with scale invariance. We argued we probably have a traceless stress tensor. And from that, we extracted a larger than usual collection of conserved charges that generate some sort of funny space-time symmetries. And now, what I want to ask is, if I actually have a quantum field theory with all of these properties, sort of consequences for the actual set of local operators in my theory do I get out of this symmetry structure? So on general grounds, the local operators at any fixed point in RD furnish a representation of the charge algebra. So this is a statement that everybody already knows. When you have symmetries, the operators transform under them. Just at the risk of being too pedantic, in this language of charges as topological surface operators, et cetera, I can understand this in perhaps a more sort of visceral way by noticing that if I have a local operator, then I can surround it by a d-1 sphere on which I insert one of my charges, so make that the sigma for one of these charges. And then because that's a topological surface operator, I can sort of contract it down onto the point. So I end up with something which is still a local operator that sort of has this infinitesimal thing living around it. And that should give me some new thing that behaves for all intents and purposes like a local operator. And I write that as the charge acting on the operator. So in this picture, it makes sense to sort of think of the charge acting, taking the operator as an argument. You're probably, or some of you, are more familiar with seeing this written as a commutator. And that, again, comes from not using my full flexibility to choose arbitrary topological surfaces. And this picture sort of corresponds to a picture where I have an operator at 0, and I choose a slice like this, and then another slice like this, sigma 1, sigma 2. And then sigma 1 minus sigma 2 is homotopic to my sigma here, this small circle. So this really is the same thing as just if I choose some slice where I want to define a Hilbert space and I have time-ordered operators acting on it, the commutator is the same thing. Okay, so I get representations. What sort of representations? Well, some I already knew the answer to, because this just follows from pre-conformal field theory. So if I act with one of these momentum generators, you already, well, from the language I've been using, you know that the answer is going to be that it just gives the derivative. And that actually follows from this word identity I wrote down for the conservation of the stress tensor earlier on. This is because this thing was the contact term appearing in that word identity, because the integral of the divergence of the stress tensor is the thing that I get when I use Stokes' theorem to relate the contour integral on the little ball to something that actually hits the operator. Similarly, let me introduce an operator that has spin. So A is some Lorentz index. then these rotation generators indeed act by rotations, where I've introduced some matrix S, which satisfies the same commutation relations as my M's, but in the representation in which O transforms. So my local operators in a QFT live in some irreducible representations of the rotation group. So this B is the index for some appropriate irrep. The newer things, first are the dilatation operator. And this dilatation is the thing that's supposed to generate infinitesimal rescaling. And so the contact terms that I get here encode, what did you call them, Silvio? Y's? So this is like D minus Y? Okay. So this encodes the infinitesimal scalings of these operators, their scaling dimensions, which in Silvio's language is the difference between the dimensionality of space-time and this Y scaling of couplings that you would get if you tried to introduce these operators into the Lagrangian. So this is Silvio. Okay, so delta is the scaling dimension. And now, to say something about the action of the special conformal generators, I want to first make an observation about the conformal algebra in connection with this idea that the eigenvalues of D are the scaling dimensions. From the algebra on the right board, you can very quickly see that the dilatation acting on the thing that I get by acting with a special conformal transformation on O the scaling dimension of this thing is one less than the scaling dimension of the original operator. And similarly, for momentum, also known as derivatives, the dimension increases, the scaling dimension increases by 1. So the K's and the P's are like lowering and raising operators for scaling dimensions. And now I'm going to assert, and this, if you get really, really technical, this becomes something that you can question, but for an appropriately generous interpretation of the phrase physically sensible, in physically sensible theories, the scaling dimensions are bounded below, meaning you don't have operators with arbitrarily negative scaling dimension. You may already have an intuition that the scaling dimension should actually be positive, and we'll see later on that in unitary theories, in Euclidean theories that are related to unitary theories, in Lorentzian signature they have to be positive. But more generally, if your scaling dimensions in a non-unitary theory are unbounded below, things get pretty hairy. So we'll only pay attention to theories where they are bounded. That means that if I start with some operator of definite scaling dimension and act with K's enough times, eventually I have to get 0. This is like the reasoning for constructing representations of SU2. So that leads to the definition of a conformal primary operator O is one such that K mu O inserted at the origin is equal to 0 for all the mu's. So it's sort of at the bottom of some tower of operators with scaling dimensions that increase. And similarly, we define a conformal descendant is O such that there exists O prime with O equals P mu of O prime. So this is just saying that a descendant is a derivative of something. So we now can put together something of a picture of the kinds of representations of the conformal algebra that we're looking at. They're going to start with primaries. And these are some operators. And in principle, I have sort of horizontal action amongst primaries given by the rotation generators. So when I say I have a primary, I mean I have an SOD representations worth of primaries. And then I act with derivatives, and people refer to how many derivatives I have had to act on the primary with to get to the operator I care about as the level of the operator. So one derivative on a primary, I get level 1 descendants. 2, I get level 2 descendants, et cetera. And if you're a representation theory person, you might notice that this is a kind of a Verma module for the conformal algebra, and if you don't notice that, then it doesn't matter. Okay.
Would you define a primary just with the condition on the case, or with the other conditions that have been well-defined eigenvalues in terms of scaling and rotation?
Right. So I made an assumption that there is such a number here. In other words, that the dilatation operator is diagonalizable. In non-unitary theories, this is not the case. So I think your question is related to the question of whether all operators are either primaries or descendants. And in a unitary theory, you can prove that they are. We will see some of the info that would go into that proof over the course of the rest of today. In non-unitary theories, it doesn't have to be the case. So in non-unitary theories, for example, you can have a dilatation operator whose action on the set of operators in your theory has sort of a non-trivial Jordan block structure. And then there are operators that are neither primary nor descendant. And then things get messy. But I should say that compared to what I was saying before about wanting the deltas to be bounded from below, although those theories I'm mentioning that have this Jordan block structure can be annoying, if you do care about non-unitary theories, they're fine. It's legal. Okay. So this was the action of the conformal algebra on operators inserted at the origin. And that was a meaningful specification because my definition of my charges knew what I meant by the origin, right? In contrast to something like just momentum generators that sort of you can move any point to any neighboring point. I had, for example, this dilatation transformation that dilates that sort of expands everything around some point that I called the origin. So there's going to be a different action of these conformal charges on operators at general points. But it's determined in terms of the action of the origin and the conformal algebra because I can think of an operator inserted at some other point as arising from the exponentiated action of the translation operator, of the infinitesimal translation operator on the operator at the origin, which means if I want to act with a conformal charge on this guy, I just need to know how to commute him through this exponentiated thing, which I can do using Campbell-Baker-Hausdorff or whatever. So I'm just going to state conclusions because these calculations are not interesting. So as you would expect for momentum generators, there's no difference. The momentum killing vector doesn't know what the origin is. Rotations act as they did before. Remember, this S is sort of the internal rotation matrix that acts on the Lorentz indices that I'm now suppressing on this operator. But now there's an extra explicit factor where this lowercase m mu nu is the killing vector for rotation. So this acts by derivatives on this thing. So this is what you would expect if you have an operator that's not at the origin and you do a rotation. You have to sort of change the frame that acts on the indices, and you also move the operator, which acts with derivatives. Dilatation. Again, there's sort of a pattern here. Again, you get the scaling dimension, but you also get a factor of the conformal killing vector acting on the point. And K mu. In this equation may or may not be relevant if you choose to do one of the exercises. Of course, you can also look it up in books. Plus x nu s nu plus I. This is gross. Okay, that's gross, but that's what it does. Notice that there's an isomorphic conformal algebra that sort of thinks of x as the origin, that acts on these operators in the usual way, in the way that these did. It's just that I've chosen some particular way of writing, of sort of choosing a basis. It's not quite a choice of basis. The difference between this algebra and the algebra that would treat these things like they lived at the origin is you have to conjugate by elements of the group. I mean, that's exactly what's going on here. You have to conjugate by the translation operator that would then sort of move things back to the origin and then act in the usual way. Okay. So, because I'm not willing to speak for 2.5 hours nonstop, I will now ask for questions and then declare an unscheduled break for 10 minutes before the second half of my lecture, because for some reason they scheduled for me for 2 consecutive lectures. So, are there any questions?
That's only for primaries, right? The bottom one?
This is for primaries, yes. Sorry, right. Everything for primaries. Of course, if you didn't have a primary already at the origin, acting on the operator would give you this sort of parent, this inverse descendant, and then you would also get that sort of corresponding O prime, whose derivative is O in this transformation. But it's easier to work with primaries all the time. We'll see even more reasons that you should work with primaries all the time momentarily after we return from the unofficial break. Yeah.
That in general, they don't have the inversion symmetry.
Sorry?
In general,
normal CFTs you said previously that they don't have the inversion symmetry.
That's right.
But are there any physical theories that we care about that they also have inversion?
That do have inversion, yes. There are lots of theories that have inversion and lots of theories that don't have inversion.
But CFTs?
Yeah, CFTs. So in a CFT, the inversion symmetry is continuously connected. You can conjugate by actions of by elements of the conformal group, and this is an exercise you can do if you're interested. You can conjugate by elements of the conformal group and turn an inversion just into a spatial reflection. So if you have a theory that doesn't reflect parity, then it can be a conformal field theory, but it won't have inversion symmetry. Whereas if you have parity symmetric conformal field theories, they will. And there are lots of theories, conformal field theories, that are not parity symmetric. We know how operators fit into representations of the conformal algebra, at least under nice conditions. We know how to act on the operators at the origin and also at other points. One more thing. So the last point, just on the issue of how operators transform, is to ask about the transformation of operators under finite conformal transformations. So the operators at a point represent the conformal algebra, which is SOD plus 1 comma 1, but the operators at all points represent the conformal group with capital letters, SOD plus 1 comma 1. So we should ask what sort of representations they live in. There's an answer just on fairly general grounds that I'm going to write this down so people have seen it, but I'm not going to use this particular technical fact. But there's a name for the kind of representation the local operators live in, given the fact that you can define the representation of the algebra at a point, and you know how they transform under the subgroup of the conformal group that fixes the point, so the subgroup generated by Ks and the dilatation and the rotations. So there's a name for these representations. They're called induced representations. I'm just saying this so you know that there are names for them, where H is the subgroup of SOD plus 1 comma 1 generated by rotations, dilatations, and special conformal transformations. So this is the set of generators that fix the origin. So this is the so-called isotropy subgroup of the origin. And RH is the rep of that, in which the primary transforms. So notice the primary stays a primary under the action of these things because I include the Ks but not the Ds. Or sorry, not the Ps. Okay, that's just a naming so you know where to look up the representation theory of these things if at some point that's what interests you. What is more relevant for the future point of view of computing correlation functions, which will eventually be our goal, is to actually write down equations for how an operator, which we will take to be a primary, transforms under a conformal transformation that takes x to some point x prime. And I guess I decided not to do this calculation. The answer is simple, and you should know that the answer is simple because we chose to study a primary. So this is an equation which is true for primary fields. And in some sense, you should read this equation as being the simplest thing you could have invented. So the operator O has some scaling dimension. We know that under the change of coordinates, there's this local rescaling and rotation at a given point. And this tells you that the operator prime is just the rescaling of the original operator with powers of the scaling dimension. And then it's acted upon by the rotation matrix at that point, where R is the representation in which O transforms. So this is sort of the minimal thing that you would define for an operator to transform nicely under a conformal transformation. And in many treatments of conformal field theory, this is just the asserted definition of primaries because it's so nice. And then you can work out the algebraic transformation properties by doing small transformations. So just to write down a handful of equations, so you see them a little bit more explicitly, although I don't know that it is super illuminating. This means that if you have a primary scalar of dimension delta, then it just goes to an overall scaling of itself, which it may or may not be relevant to you in your life, but it's sometimes useful to know that this scaling factor is the dth root of the determinant of the Jacobian. So you can think of this as the definition in a way that sort of explicitly is determined by the form of the coordinate transformation, instead of thinking about these omegas. Similarly for a vector, you have this thing, which again you can write down in terms of the explicit Jacobian. Which is sometimes nice to write this way, where you can see that you actually contract the vector indices with explicit factors of the full Jacobian as a matrix, and then you have a slightly smaller scaling factor. And you can generalize that to traceless, symmetric traceless tensors pretty easily, or even other things. And I've just written these down now because tomorrow, we're going to come back and spend a lot of time talking about the constraints of all of this conformal invariant stuff on actual correlation functions. And then the Ward identities imposed by conformal invariants can either be put in some sort of differential form where you look at infinitesimal transformations and act that they be invariant, or you can just ask for functions that sort of transform appropriately under finite conformal transformations like this. Okay, but the plan for today is not correlation functions. The plan for today is operators. So far we have operators that live in various vector spaces. We have operators at a point that live in a vector space that represents the algebra. We have sort of this giant collection of operators that live at all possible points, and that represents the group. But there is additional, I'm not using the board very well. There's additional structure on, let me call it V, the vector space of local operators at a point. So this is the thing that represents the algebra. And that additional structure is that V is a Hilbert space. And here I'm finally explicitly using the fact that what I'm interested in today is Euclidean theories that are related to unitary Lorentzian theories by some analytic continuation. So the claim is that the vector space of local operators, this is almost true, it's some sort of topological completion of the vector space of local operators, is the same thing as the Hilbert space that my associated unitary theory, so unitary theories have Hilbert spaces, attaches to a d-1 dimensional sphere spatial manifold. And this isomorphism is known as the operator state correspondence. So this is a bijection. It's an isomorphic bijection. So given an operator at the origin, I should be able to produce a state. And given a state in this space of states on a d-1 sphere, I should be able to produce an operator. The first part is just a picture. So given an operator, I can draw a d-1 sphere around it, and for lack of a better term in the language of sort of abstract quantum field theory, I can do the Euclidean path integral, whatever that means if I haven't specified fields. I can sort of do the thing that Euclidean quantum field theory does on a ball and end up with some state that lives on the boundary. That I will label by the name of the operator. This is in the space of states. It's attached to the d-1 sphere. I've been writing 3 or d-1. This is in the space of states attached to the d-1 sphere. And I haven't really given you the Hilbert space structure yet, but we'll get to that in a minute. So far, it's a space of states. And note that by construction, the charge algebra acts on these states as it does on the operators inserted at the origin, because to act on the state, I first build the state, and then I insert one of my Q's here. But then this was constructed by some sort of Euclidean path integral over this ball, where I didn't insert anything away from the origin, so I can shrink it down. And then I just transform the operator to the transformed operator and get the state associated to that. I guess I'll do it here. So then so this is actually, you might notice that this is an operation that didn't use conformal symmetry at all. In any Euclidean field theory, there's some sense in which you can assign a space of states to a d-1 sphere, and then there is a map from local operators to states on that sphere, given by doing the Euclidean path integral, or whatever that is. And the interesting thing in a conformal field theory is that we're going to actually have an isomorphism, and further that we're going to have a Hilbert space structure on the space of states, and the Hilbert space structure helps us build the isomorphism. So this becomes the more interesting part of the construction. I want to be given a state, I'll call psi because it's some general thing, and I want to construct some operator at the origin that I could insert that is going to be the inverse of this operation. So I need an operator that if I insert it and then do the Euclidean path integral again, I'll get back my original state. And now a key fact, and I haven't described the Hilbert space structure yet, but just trust me, I'm going to get to it. Because this thing is because this state lives in a Hilbert space, And because it is a normalizable state, which I guess is also something that I'll explain later, but it should sound plausible, I can decompose it in an orthonormal basis of states that are eigenstates of the dilatation operator. And now, the slightly tricky claim is that for each one of these states, for each state appearing in this sum, I can now do an inward path integral evolution from the state out here back to here. Now, normally this is a bad thing to do in a Euclidean field theory. Doing time evolution, and so this Euclidean path integral is sort of doing a Euclidean time evolution in the radial direction, and doing inverse time evolution in Euclidean field theory is a bad idea because it is acting with an unbounded operator. Sorry, you're about to ask a question.
So the states already we define. I'm okay that this thing is equal states, but how do I move it on a complete basis so that I can do this expansion?
You want to know why the eigen? Sorry, you're referring to the states I build this way.
So
I haven't done this. I haven't built the operators yet. So maybe I should have called these psi i's. I haven't yet committed.
Why this is complete basis?
I have a Hilbert space. Okay. See, I knew this was going to come up. So this is related to the question of whether you can diagonalize the So I've already made an assumption that I didn't tell you, although it sort of came up before, which is that I can diagonalize the action of the dilatation operator on this Hilbert space. I don't know the minimal possible set of assumptions that you can make to prove that that is the case, but it follows if you believe that the partition function of your theory on SD minus 1 times S1 is a finite number. Which is something that is true in practice. That tells that partition function takes the trace of e to the minus, say, beta, where that's the radius of the circle, times the dilatation operator, or I guess in this case, I times the dilatation operator. And if that is finite, that means that operator is a trace class operator, which means it can be diagonalized. And that means that you can diagonalize the thing the Hermitian operator that it is the exponential of. And now you can diagonalize all states, and now you just have a Hilbert space with a diagonalized operator, and you are going to expand all states in a basis of those diagonalized states. So I think that if you grant me this fact about partition functions at least, then I win. And okay, is there a smaller set of assumptions is an interesting question. As I was telling some people during the break, this is the fun and also the vice of this very abstract way of thinking about conformal field theory that this sort of Bootstrap community is endeavoring to do, is that we don't really know the right axioms. And there's many things that are just true in any example that you will ever come up with, because we only have so many ways of coming up with examples. And then you believe them, and then you can either make that an axiom or hope that you're going to play a game where you find a more minimal set of axioms. I'm going to take it to be true. I'm going to at least take this partition function statement to be true. Where was I? Right, so now I have this basis of states. Now I have this decomposition into states that are acted upon simply by the dilatation operator. And now even though the inverse Euclidean time evolution into this ball is a bad thing to do on general states because it's an unbounded operator. On these states, it's fine because it's just multiplying by e to the lambda delta I. Which indeed is growing. So this is the reason that it could be bad if I had an infinite sum of operators with arbitrarily increasing dimension. But for each individual one, this is fine. Now at this point, you could stop me again and say, well, how do you know you don't have an infinitely increasing sequence of things? And therefore, something will go wrong when you try to evolve the whole state in. And that actually happens because if I had started out with an operator here instead of at the origin, then it would also give me some state. And that state would actually be an infinite sum of eigenstates with increasing dimension. And then you see why you can't Euclidean evolve back in, because at some point you hit the operator, and then evolving past it isn't something you can do while still sort of getting towards a local operator. So there's some nuance to this statement that you should really focus on finite sums of eigenstates. And this is some basis for your Hilbert space. So it's saying that as long as you construct some correspondence between local operators at the origin and a basis for your Hilbert space, and then you can further construct arbitrary elements of your Hilbert space that will correspond to operators that live at other points. So this is more detail than I think is usually discussed in the context of the state operator correspondence, but this is what is really going on, is that you're looking at this basis that diagonalizes the dilatation operator, and finite sums of states of that form are things that correspond to literally local operators in the origin.
Sorry, at what point did you need the analytically be able to analytically continue to Lorentzian theory?
I keep saying the words Hilbert space.
That's when.
And the fact that this set of states actually has a positive definite inner product is something that I will now argue follows from continuation to Lorentzian signature. Right? In a general Euclidean QFT, that's not something you get to assume for sort of the space of states assigned to a random d-1 sphere.
One other thing you said, if that operator wasn't at the origin, your expression would blow up. Can't you rewrite that as an operator at the origin, like as a sum of a bunch of operators at the origin?
Yeah, that's what's happening. But you don't get to call it an operator at the origin. It doesn't have the locality properties of the operators at the origin.
For this purpose, I think it would be good to repeat questions.
Oh. That question, what was your question again?
One of them was, why did you need Lorentzian continuation? The other one was, can you rewrite that operator that's not at the origin?
Okay, the first question was, where did I need the fact that this is related by analytic continuation to a unitary theory in Lorentzian signature? And the answer is that I keep saying the words Hilbert space. And although I haven't talked about it in depth, and depending on timing, I may or may not talk about it in depth, the fact that there is a Hilbert space structure here does follow from the existence of a Lorentzian theory. The other question was, why can't I just rewrite this operator as a sum of operators at the origin here? And the answer is that in a sense I can. And this is something that we'll get more into when we talk about the operator product expansion. There's a formal sense in which I can write this thing as e to the I p dot x acting on O at 0, and then I can expand this in a power series and get some infinite sum of derivatives. The issue is that you really shouldn't call that thing, that infinite sum, a local operator at the origin, because local operators have certain locality properties. Their singularities with other operators only occur when the other operators are on top of them. So even though you can write this in this way, and there's a sense in which this is true, it's precisely this Hilbert space sense. It's that these individual states correspond to states in the Hilbert space, and then there's another state that corresponds to inserting the operator here. And the state you get from that operator there is what you get when you take the convergent sequence, you take the convergent sequence of states that you get from this expansion. But that's really in some sense, the point is that if that formal expression that you believed to be true really starts to make sense once you have this picture of the Hilbert space that has an orthonormal basis. And you can look at convergent sequences that then give you other elements of the Hilbert space. Okay. So how do we see the Hilbert space structure? I've been asserting it, and it seems at least plausible that if you have some space of states in the Euclidean theory, and the Euclidean theory comes from continuation of Lorentzian theory, that there's some Hilbert space structure. But a Hilbert space actually tells me how to compute norms and how to take adjoints of operators and things. So I should ask how to expose that. And the best way to do it is to notice that this D-1 sphere, where this Hilbert space is supposed to live, in a Lorentzian context, it wants to live in the space R times SD-1. Right? If you wanted a Lorentzian theory that somehow naturally gave you a Hilbert space that lived on a given slice, you want your Lorentzian theory to live on time times that slice. And then the key is that RD minus the origin is equivalent up to a Weil transformation. So now we're back to these Weil symmetries that I said I was going to use eventually, is equivalent to this. And I'm not going to write out the algebra, but it's the case that ds squared, the metric on RD, is equal to E is equal to, how should I write it? R squared ds squared on SD-1 times R, where the time coordinate tau here is related to the radial coordinate in my Euclidean space as the exponential. So R is the log of tau. So this tells me that up to issues of Weil anomalies that I promised to ignore and to assure you that they don't meaningfully modify this statement, this tells me that correlation functions of my, well, maybe I should say generally, the Weil symmetry tells me that up to worrying about Weil anomalies, that I have a relationship between correlation functions of this type, where I can do a Weil rescaling of the metric at the expense of these extra factors that come from the rescaling of the operators. So this tells me that in the case of the cylinder, I can define the following operators that I call cylinder operators in terms of the flat space operators inserted at the corresponding coordinate. Here n is some unit vector that tells me where I am on the sphere, and tau is the time along the cylinder. And then correlators between these cylinder operators and these flat space operators agree. I've just absorbed this factor of omega, which is e to the delta, which is e to the tau in these cases. So this tells me that tau 1 and 1 dot 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 on the cylinder is equal to O flat of x1 dot 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 on RD. So I now know how to relate correlation functions in RD to correlation functions on the cylinder. But correlation functions on the cylinder are transparently related to things that I get by analytically continuing from a Lorentzian theory, because this cylinder is where I can define a Lorentzian theory on SD-1 times Lorentzian time. And then analytically continuing that time parameter, the cylinder time, is going to give me the Euclidean cylinder. So I don't know, 1 or 1:30?
Don't say that you have 25 minutes.
25 minutes, okay. So I want to use this relationship between Euclidean physics and Euclidean correlators to Lorentzian physics and Lorentzian correlators to expose the Hilbert space structure on this space of states. So I need to recall how unitarity, which is my code for the existence of this Hilbert space with a positive definite inner product, et cetera, how unitarity is felt in Euclidean, in the Euclidean continuation of a theory. So in the Lorentzian theory, I have operators which I can meaningfully describe as Hermitian. That, as usual, are obtained from operators inserted at the origin. And I can define a Hermitian operator as one which is equal to its own Hermitian conjugate at the same point. That's because if an operator is Hermitian at the origin, and I Hermitian conjugate this whole side, then I switch the orders, the i's flip, and H and P are Hermitian in a unitary theory. So I get back an operator at the same point, which is the parallel translate of, sorry, maybe I should have written it this way. O of Tx dagger is equal to O dagger of Tx. Or what I mean by this is the Hermitian conjugate of this operator, and what I mean by this is the Hermitian conjugate of the origin subsequently moved to the point T and X. And this tells me that there's no ambiguity. Because these are the same thing, I don't need to be careful about whether I talk about Hermitian conjugating before moving or not. Notice that then after Wick rotation, that defines T equal to minus I times the Euclidean time, that this isn't going to work the same way. If T is equal to I tau Euclidean, then I find that O Tex is equal e to the H tau Euclidean minus I P dot X, O of 0. And now when I do the same Hermitian conjugate game, I Hermitian conjugate the operator at the origin. The P's flip accordingly, but the T's do not. And this tells me that the conjugate of this operator is the translate of the conjugate or conjugate operator at the origin in the minus, in the opposite direction in time. So Hermitian conjugate moves things from positive Euclidean time to negative Euclidean time. This means that the requirement of unitarity, which in particular tells me that in a Lorentzian theory, that if I take the operators O1 through whatever acting on the vacuum and create a state, then the norm of that state is measured by then acting with the Hermitian conjugate of the collection of operators. This thing's supposed to be positive. And in a Lorentzian theory, to actually compute this, to think of this as some sort of path integral, if these things live at different times, say O1 through On are time ordered, then these things are anti-time ordered. because they go in descending order after I do the Hermitian conjugation. So there's some out-of-time order correlator that measures this thing, which is a disaster if you're me. I mean, some people love these things, but it's at least weird. It's like not as simple as you might want it to be. And the beautiful thing is that in the Euclidean theory, the consequence is that, so that now let me do it explicitly, O(n) dagger of minus tau n, O1 dagger minus tau 1, O1 of tau 1, O(n) of tau n is positive semi-definite. And now, if these things are Euclidean time ordered at negative time, which I didn't say but is what you should do, then when you get to the middle, you flip, and then you continue in Euclidean time ordering. So this is a Euclidean time ordered correlator. So one of the beautiful things about analytically continuing to Euclidean signature is that the things that you need to compute norms of states and to check unitarity, are the things you want to compute. They are Euclidean time ordered correlators, which are just ordinary Euclidean correlators, not some weird out of time order jazz. Okay, in this principle, you can see that what's going on is that this condition that this thing be positive tells me that if I have some collection of operators that I inserted in sort of the past of something that I call time equals 0 in Euclidean time, then what I'm doing is reflecting across to future time, and this is known as reflection positivity, the requirement that this be positive, and you've probably heard that reflection positivity is the Euclidean version of unitarity. Okay, so this tells me that I have this funny rule for doing conjugation, for taking Hermitian conjugates or adjoint versions of operators once I've analytically continued. Now I can do this on the Euclidean cylinder, on the Lorentzian cylinder going to the Euclidean cylinder. This tells me that O cylinder at tau n dagger is equal to O cylinder of minus tau n, where this is now a Euclidean cylinder operator, so these taus are Euclidean cylinder time. But now I knew how to relate these cylinder operators to flat space operators. So this tells me that even the operators in flat space I can think of as acting in some definite way relative to this Hilbert space structure. I know how to do the Hermitian adjoint of an operator acting on the Hilbert space when my operator is formulated in Rn, Rd. Yeah. Yes. The question was, am I assuming that O is self-adjoint? And I was until I changed what I'd written. Okay, so this is 2 steps of algebra to take this and unpack both sides in terms of flat space operators. And the result is nice, that if I have a flat space operator at some point x mu, dagger, then I get some scaling factors times the daggered version of the operator at the inverted position, which is not entirely surprising. I've reflected through the unit sphere, which is where I think of my cylinder. My cylinder was sort of taking Rn and vowel transforming it to this cylinder so that time equals 0 turned into the unit sphere in flat space. And I should write down, so it's been written down, the version of this which follows from just being a little bit careful about the case with spin. Leonardo's going to love this. Dagger B1 through BL at x over x squared, where these guys are our friends, the inversion tensors, which essentially acting on sort of tangent space indices reflect the direction that goes radially. Okay, and the usefulness, okay, so this was a sort of flash entry into the world of analytic continuation without really going into it. But the point is that once I know how local operators that act on the Hilbert space on the D-1 sphere, once I know what sorts of reality properties they can have, once I know how to take an adjoint, I can also, well, one thing is you can just impose the version of reflection positivity in flat space. But more important for my purposes right now, you can determine what the adjoints of the conformal charges are. Because the conformal charges come from integrating the stress tensor in Euclidean signature, and I now know how to transform some stress tensor in this way, where the stress tensor is self-adjoint, so the dagger doesn't appear on the right-hand side. And then it's an exercise. So you use this expression for the case of a spin 2 operator, and you write it as the integral over the sphere with the usual conformal killing vectors, and then you need to do the inversions and see what comes out. And you can check that the adjoint of a charge associated to a conformal killing vector epsilon is the charge associated to the conformal killing vector that I get by conjugating with inversions. And this in particular gives me the following conditions. Rotations are self-adjoint. D dagger is equal to minus D. D is anti-Hermitian, which is something that I've been sort of assuming all along because I've been writing the eigenvalues of D as I times delta, where there was some implicit assumption that delta was real. But now you see that it's real. And P's and K's switch. So this is much different than if I was looking at the action of these charges on not the spherical Hilbert space, but on some sort of flat slicing Hilbert space, because there we're used to the P's being self-adjoint. Okay. And now one of the nice things is that I get an immediate payoff from working this out. I can now ask for what the notion of unitary representations of the conformal algebra is, right? I'm supposed to be acting with this conformal algebra with these adjointness properties on the states in the Hilbert space, which are related to operators at the origin. But these requirements, these adjointness properties, impose some constraints. So for example, suppose I have a primary O, and I normalize the state that I get on the sphere from acting with that operator to have unit norm. I can now ask, what is the norm squared of the operator that I get when I act with p mu? Well, because I know how to do Hermitian conjugation, I have this, and now I can commute through. And this is a primary operator, so the state is a primary state in the sense that it's still annihilated by the action of the k. So I just pick up the commutator factor. And there would normally be a rotation piece, but these are the same mu. And the rotation generators are antisymmetric in the mu's and nu's. So I just get this, which is equal to 2 delta. For the way I've been defining delta. And so now I've found out that delta has to be a positive number in a unitary theory. You can do similar computations without an enormous amount of trouble. I won't work them out. So if you have a scalar operator, you can compute the norm squared of this state coming from acting with the charge version of sort of the box operator, del mu, and you get something proportional to this coefficient times the norm of the original operator. And we see that for this to be positive, there's a lower bound on the conformal dimension of any scalar operator, which is d minus 2 over 2. You immediately recognize that that's the dimension of a free scalar, so you can't go lower than a free scalar. You can also look at the norm of a state that you get by acting with some primary, which is in a symmetric traceless spin L representation, and then taking the divergence of that operator. So contracting 1 d mu. And this now is proportional to this quantity that depends on delta times stuff that's necessarily positive. And you get another unitarity bound. Delta equals L plus d minus. Delta is greater than or equal to L plus d minus 2. And this is for something that has spin. So spin greater than or equal to 1.
Why in the first case delta cannot be 0?
In the first case,
That's the next case.
yes. Delta can be 0. In the delta equals 0 case, we showed before. Okay, I was going to. The question was why delta couldn't be 0 to the recording. Delta can be 0, but now we're about to say how to interpret. Okay, so or delta equals 0, but now these two cases have much different interpretations. So how do we interpret the case where one of these bounds is saturated, where delta is equal to 0 or equal to d minus 2 over 2, or in the spin L case, delta is equal to d plus L minus 2? In that case, this state that I was building in this way has norm 0, so it's not a physical state. So that tells me that I have some operator equation that tells me that this derivative acting on this thing is equal to 0, or this box acting on this thing is equal to 0. So if delta equals 0, the thing I erased before this showed that meant that the derivative of the operator was equal to 0. This is just an ordinary derivative, not contracted with anything. So the only operator for which that's true is the identity operator. So indeed, in the second case, you can still solve it with delta equals 0, but it's this degenerate case that you already took care of. If delta is equal to d minus 2 over 2, it means that you have an operator that obeys the equation of motion of a free scalar field, box phi equals 0. And indeed, it turns out that it means that this is a free scalar. And in this case, d plus L minus 2, you find that d mu O mu 2 up to mu L is equal to 0. This is a conservation condition. In the case when L is equal to 1, this just looks like an ordinary conserved current. This tells you that an ordinary conserved current, which is a vector, has to have dimension d minus 1 in a unitary conformal field theory. More generally, these are some sort of higher spin conserved currents that normally only appear in free field theories, and I won't discuss them. Sorry? Oh yeah, the L equals 2 case is the stress tensor. Okay, so in my last bit, okay, so now we have operators. The operators are isomorphic to states in a Hilbert space. We understand how unitarity manifests itself in that Hilbert space, how the positive definiteness of the Hilbert space and adjointness properties of operators is manifested. And now one more thing. The last sort of pure structure on operators before we get into computing observables, which will be tomorrow, is that this space of local operators has even more structure. So V, which turns out to be a Hilbert space, has an algebraic structure in the form of the operator product expansion. And this just comes automatically from the operator state correspondence that we had before and the various good properties of Hilbert spaces. So let me consider two operators at two different points. And of course, by the same general structure of what Euclidean theories give me, this gives me some state. In this Hilbert space that I associate to a d minus 1 sphere that I draw around the operators. And now I just do what I was doing before with individual operators when I was arguing that there was an operator state correspondence. So now these multiple operators give me a state that can still be expanded with some coefficients that can depend on the position in terms of eigenstates of the dilatation operator, which we argued before can be shrunk down to find individual operators that I could insert. We can do a little more. We can organize this into primaries and descendants. Because descendants just come from acting with p's on the primaries. So this is equal to the sum over all primary of some sort of polynomial, which I'm thinking of as a differential operator because these p's are sort of like derivatives, acting on the state associated to the primary. So this was an expansion of a given normalizable state in an orthonormal basis for my Hilbert space. This is often written at the operator level as sort of a multiplication of operators, which is just sort of the same thing where x1, 2, derivative at x2 of OK at x2 these are these same polynomials in x's and p's, where now the p's are acting on the operator instead of the corresponding state, so I can write them as just derivatives with respect to the insertion point. And this is really, this is code for this. And the reason that it's useful to have that point of view is that it tells you where this is a valid thing to insert. Because this is really telling you about convergence of a sequence of states in this Hilbert space associated to this sphere. So if I had another operator, let me make it even worse. If I had another operator inside the sphere, then this is illegal. This is not a meaningful expansion when I'm expanding in this Hilbert space, because I needed the state that just came from these guys. Another way of saying it is that once I make this replacement of operators, if I studied correlation functions where I had this third operator here, then the expansion wouldn't converge. And then as the final point, let me just comment on the flexibility of this construction. Because the thing that I wrote down here, if I wrote it correctly, yeah. The thing that I wrote down here involved doing exactly what I drew, where I put one operator at, well, the origin and one at x, or when I wrote it in the equations, it was putting one at x1 and one at x2. And then I'm expanding in the Hilbert space defined on a sphere surrounding x1. But if I had this annoying third operator here, and I was planning to study this configuration, and I wanted to use this operator product expansion, I could have drawn a big circle this way, centered at some other point. And it would still be the case that doing the Euclidean path integral on this ball gives me a state associated to these two operator insertions, which I can still expand in an orthonormal basis. And it's going to have to converge because this is a normalizable state, and it's going to converge in correlation functions with stuff on the outside. So the nicest formulas, and the ones that you usually see in papers and in the books, correspond to this particular choice of expansion, where you do an OPE and you expand in operators at the same point as one of them, or equivalently in the Hilbert space centered on one of those points. But you can actually work much more generally as long as you can find a sphere to surround the two operators you care about and not other operators. OK, so that's all I have to say today. This structure is something worth exploring. Tomorrow, we're going to talk about using it. Amongst other things, we're going to talk about using it in order to actually set up the computation of correlation functions. But something that you should look at today, if you feel like looking at the problems, is the interesting question of how conformal symmetry constrains this differential operator that somehow encodes all of the stuff that's appearing in the OPE. Questions? Yeah.
Can you comment on the case where these three operators will become collinear?
I'm not sure I have anything to say about it. Collinear seems fine to me. I can still, maybe I'm not understanding. You just need to find some circle to draw. If the question is whether something is useful, you just need to find some circle.
O3 is exactly in the line between O1 and O2. Which circle would you
Oh, that's, okay. The question is, if I want to take the OPE of O1 and O2, and I have in mind to use it in the case, if for some reason I want to do this, and I have in mind the case when there's a third operator, O3, on the line, exactly on the line connecting O1 and O2, is there something useful I can do, I guess is the question. I can do conformal transformations. So if there's nothing else, if there are no other operators around, it depends what else is there, because I can do conformal transformations, and I can get this guy out from in between these two guys. But then if I had something else somewhere else, it could, you need to worry about it. But if it was just for considering a 3-point function like this, you can basically move 3 points anywhere you want, so you can get them apart from each other.